We are pleased to have Almir Silva Santos from Universidade Federal de Sergipe, Brazil, who is going to talk about blow-up analysis of large conformal metrics with prescribed Gaussian and geodesic curvatures. Welcome, Almir.
Thank you. Thank you. Good afternoon. First of all, thank you for Raíssa for the invitation again. Thank you for sending me. Today I'm going to talk about the block analysis, which we worked in my last year. Is a joint work with Raíssa and our friend Cruz from Federal University of Alagoas. Let M be a Riemannian manifold with boundary. Associated to this metric G, there are two functions, Gaussian curvature and on the manifold and the geodesic curvature on the boundary if the dimension is equal to 2. And if the dimension is bigger than or equal to 3, there are the scalar curvature and also the mean curvature on the boundary. So associated to the metric, there is these two functions, the Gaussian geodesic and scalar and the mean curvature. And these two functions satisfy these two properties. It's important. They are invariant by diffeomorphism, and they also satisfies this scalar invariant here. So the question is, which functions it's realized as the Gaussian, the geodesic, the scalar curvature, and the mean curvature. This is the prescribed curvature problem. I don't know what's happening. No problem. No problem. Okay, thank you. The Gaussian curvature is a particular case of the scalar curvature, only has this naming on dimension 2. And the problem that we are interested in is the prescribed curvature. Firstly, in the closed case, when the boundary is empty and the manifold is compact, we can study this problem in 3 different ways. Give a function on the manifold, you can ask if there is some metric such that this function is the scalar curvature or the Gauss curvature, depends on the dimension of this metric. We can also ask if there is some conformal equivalent metric to the affixed metric, which has this function f as the scalar Gaussian curvature. And also you can study this problem in the conformal set. Two metrics are said conformal if there is some positive function satisfy this condition. G and G dot are conformal if they satisfy the relation. And it's conformal equivalent if there is some diffeomorphism of the manifold such that these two metrics are conformal, right? The presence of the diffeomorphism gives us some freedom to solve a problem that you cannot solve in the other sets. It's clear that the problem C implies B that implies A, but it's not true. The reciprocal is not true. There are examples that you can solve the problem here, but you cannot solve here, and you cannot solve it here. And also, B doesn't imply C. So it's a problem, three problem that it was a lot. There are a lot of works on the literature. And the first case, it's when the function is constant. It's a famous problem. In dimension 2, you have only the uniformization theorem. And if the dimension is bigger than equal to 3, you have the Yamar problem, which was solved by the works by the Yamar, Trudgen, Elban, and Shen. And you can see a beautiful work, resume of these works in this paper by Lee and Parker. And when the function is not necessarily constant, up to our knowledge, the first paper that studied this case was by Berger in the 71. And the later, in a series of paper, was studied by Kasdan and Warner in the 70s. There are 6, 7, 8 papers about this problem. And in the 87, Kobayashi considered this problem with a restriction on the dimension. He asked if give a function if there is some metric such that the volume is unity with unit volume. It is interesting because the problem is not conformal, but his technique uses heavily the tool from geometric conformal geometry. It's a beautiful work, but he proved a lot of cases, and in 2014, Matsuo closed this problem. So there are a strong relation between the topology and this problem. In dimension 2, we have the well-known Gauss-Bonnet theorem that gives us some condition. The integral of yet in the dimension 2, the integral of the Gaussian curvature is a multiple of the Euler characteristic. Then we see that if some function f is the Gaussian curvature of some metric on the manifold, then when the Euler characteristic is positive, then the maximum of f has to be positive. And also, if the Euler characteristic is 0, then the function has to be identical to 0 or has to change sign. And if the Euler characteristic is negative, then the minimum of function has to be negative. In 75, Kasdan and Warner, in one of the paper, they proved that this condition, if you have satisfied this condition, then this condition are sufficient condition to the existence of some metric which is conformally equivalent. In the conformally equivalent case, that is, if you have satisfied this condition, then there is some function and there is some diffeomorphism such that this metric has f as the Gaussian curvature. So the conformally equivalent case is completely solved by this work. What about the boundary case when the boundary is not empty? So we start here with with a compact manifold with boundary in dimension 2, and they give a function on the manifold in one, and another one in the boundary. Is there some Riemannian metric such that the Gaussian curvature of this metric is f, and the geodesic curvature is the other function? Also, you can study this problem in general case, in the conformal equivalent case, and in the conformal case. Also, you have the Gauss-Bonnet theorem, restriction between the relation between the geometry and topology, and at least when of the function is equal to 0, you have the same condition on the function, the same condition. And here I put only the case that the Gaussian curvature is identical to 0, but you have the same condition in the geodesic curvature also are zero, is zero. This work proved that these conditions are sufficient in general case. I mean, if you have some function satisfy one of these conditions, then this function is a Gaussian or the geodesic curvature of some metric. Doesn't matter which metric. Was proved by Tiarlos and Feliciano in this work in 19. And recently, we proved that these conditions are sufficient also in the conformal equivalent case. You can find a function, you can find a diffeomorphism such that that condition are sufficient to solve the problem in the conformal equivalent case. And also, we study this problem. We ask for a restriction on the volume or on the area of the boundary. In this case, it's in n dimension. Still, we have open problems here because we are studying only one of the functions on the manifold on the boundary is equal to 0. When you consider general function, it's not solved yet. In high dimension, the relationship between topology and the geometry is very different. It's difficult to identify this relationship, for example, but there are a lot of papers which study this case. For example, Shenyao, Gromov-Lawson studied this relationship, and they proved, for example, that in the torus of dimension 3, there is no metric with positive scalar curvature. In the closed case, it's in the closed case, and in the non-closed case was studied by Carlota and Lee, and Ezequiel and Francelle Conrado, both work from 19. They proved, for example, the result it has a consequence, which means that this to manifold there is no metric with this condition, right? So just an example. Okay. If you want to know more about this problem, you can look this work, which is on archive by Gromov for electron scalar curvature. Okay. What about the conformal case? Let's see. Give a function. Give a function on the manifold of dimension 2. Manifold. There is some function such that the Gaussian curvature is of this conformal metric. Is that function f? Oh, sorry. Yeah, just a minute. Okay. So the problem in conformal case it's this one. We fix the metric G and ask for some function such that it solves this problem here. The new conformal metric has f as the Gaussian curvature. This case can be solved by solving this PDE on the manifold. And this, it's not so easy to solve. And yet it's still an open problem. As I said, the BG was the first one to study, after our knowledge, to study this problem when F is a general F. And he found a necessary condition to solve the PDE, the problem. Casa Warner has started in 17. To study this problem, it has a lot of work about this, and many others. There are a lot of papers on the literature regarding this problem, and it's an open problem, at least when the Euler characteristic is positive, which is the hard case. This case it's called the Nuremberg problem. For example, it's well known by the Casa-Warner obstruction that this function of the sphere is not a Gaussian curvature of some conformal metric to the hard sphere, even for any epsilon, positive epsilon. Not that one is the Gaussian curvature of the sphere, but 1 plus this little function is not a Gaussian curvature of a conformal metric. The PDE, there is no solution for this function. It's a consequence of this one Casa-Warner obstruction, which I not say here. If you wanted to know about this problem, you can see this paper by Michael Anderson. Okay. So you can see that in this way, this problem, just because of this, it's not so easy to solve. Again, what about the compact case with boundary? The boundary is not empty. Give a function on the manifold and another one on the boundary. Is there some function on the manifold such that the F is the Gaussian curvature of this conformal metric and H is the geodesic curvature? Again, you can solve this problem by solving this PDE with boundary condition, and again by the Gauss boundary theorem. One condition to the PDE has a solution has to satisfy this condition, right? So if there is some you satisfying the PDE, then the solution has to satisfy this condition here, which relates F, H, and the Euler characteristic of the manifold. So this gives us some restriction on F and H. And there are many works that try to solve this problem. It was start by solving the problem when one of the function is equal to 0. And then recently in 2018, 22, 23, started to look at the general case when you have a general function f and h not necessarily equal to 0. But it's a still open problem to solve for any f and any h. This problem. There are many cases that you don't know the answer if there is a solution of the PDE. Our work is deal with the negative Euler characteristic. So from now on, I will consider this case, the Euler characteristic is negative. We started with a compact Riemannian surface with negative Euler characteristic with no empty boundary. By the uniformization theorem, we can suppose that the Gaussian curvature of G is -1 and the geodesic curvature of the boundary is equal to 0. This is a consequence of the uniformization theorem. And then the PDE that we want to solve, it's this one, right? It's the same. The same from it's this PDE, but this function is equal to 0. This one is -1. Okay. So we want to study this PDE, right? In this set, in the negative value characteristic. This PDE can be solved by phi. A critical point of this function, the PDE is the Euler Lagrange equation of this function. And you can see, as I said, if there is some solution, then this solution satisfies this condition because of the Gauss-Bonnet theorem. And you can see that in this case, in our set, if the function f and h are non-negative, then you cannot solve this problem because this sum will be non-negative, but the Euler characteristic is negative, right? So in the case of f and h non-negative, there is no solution. And also, it's not difficult to see that when the function f is positive, the maximum is positive, the function is positive at some point, then the function is not bounded from below, right? So what we have here, this is not difficult to see, is that if f and h is non-positive and not identically zero, one of them are not identically zero, then you can solve the PDE. You can equify the conformal method with f as Gaussian curvature and h the geodesic curvature. And it is a unique solution, which is the global minimum of this function. And this is because with this condition, the functional is cohesive and strictly convex. And also, in this paper, they deal with the case when with f negative, and this quotient is less than 1. They prove also that in this case, you have a solution, and when the function h is less than or equal to 0, you have the unicity of the solution. Also, we have studied what's happening with the functional in a local minimize of the functional. We do some calculation and see that the second derivative is positive definite. Okay. This implies that for small perturbation of f and h, if for this f and h admit a local minimize, for small perturbation, the corresponding functional for f and h perturbed, you still have a strictly local minimize. This is a consequence of Lax-Milgram theorem in the implicit function theorem. Now, we consider two functions f and h with these assumptions. They are non-positive. The maximum are equal to 0, and they are not identically 0, right? Now you took a small perturbation of these two functions, f and h, define f mi and h lambda, and you have the corresponding function here. By our previous results, if you have a solution for f and h, for small perturbation, we still have a solution. So we want to analyze what's happening with these perturbations when the parameters goes to 0. First thing, for the for the functions f(h), which correspond to functional I, we'll have a única, we have a única critical point, which is a global minimizer. And for small perturbation, you have a strict local minimizer by the previous results, which I'm calling U mi lambda, which satisfies this convergence when the parameter goes to 0, because all these functions are local minimizer, and U0 is the only local minimizer for the parameter mi lambda equal to 0. So you have this convergence. Also, if you fix one of the parameters, this function and U, this function is not increasing. This is an important condition for the method that you apply here. And in this case, remember that the function f is not non-positive. Then, if you take a small perturbation with mi positive, then the maximum is bigger than 0. And then, as I said, if the function f, this function is positive in some point, then the function is not bounded from below. So for the parameter is equal to 0, you have the function which is bounded from below, and it has only one global point, minimum point. And for small perturbation, the function is not bounded from below. The picture here is this one. For the function I, you have the function has a global minimum. But for small perturbation, the function is not bounded from below, but it has a local minimizing in this point, U, mi, and lambda. So you can take, you can choose a function which the energy of this function is less than energy of the minimum point. And this gives us the geometry of the mountain pies. So you consider all the continuum path that goes to this function, take the maximum and then the infimum of this maximum. And you can find another solution for small perturbation of this case. Remember, this guy, the local minimizer, converges to U dot, to the only minimize in the first case. Okay. So you consider this constant, which is the infimum of the maximum of the function along of all continuum paths that goes to from the minimum point to this function, which is the energy is below of this energy. And you can prove that this level satisfies these estimates. This is you use a test function. And these estimates, it's important to prove what you prove. A consequência of that the functional, when you fix the one parameter vary the other one, is that this function, which is defined in these ways, is not increased. This condition is important to use what is called as the Stur monotony trick. You have to analyze a family of functional which depends on some parameter. You wanted to analyze what's happening when the parameter goes to 0. Since this function here is not increased, then this function, the derivative of this function exists for almost every parameter. Okay. And then what you will have here is the existence of some critical point which is not a local minimizer of the function. Okay, but this it's the Montepière's argument, but it's an assumption that we find it's the estimate on this integral here. This, for the method, it's important, especially because this guy has some good properties. So now, if you have this solution, which is not a local minimizing, what happens with this family of solution when the parameters goes to 0? I said that this is a solution, it's a critical point, but this one converges to the global minimizing. What's happening with the other one, which these critical points? So the point here is to analyze this convergence. So the proof, it's just use the definition and find some estimates here. Okay. So now you have at least two functions, two conformal metrics. One which comes from the minimal point, local minimized minimal point of the function, and another one which comes from the critical point which is not a local minimizing. What's happened with these two metrics? This one converts to the initial metric, but what's happening with this one? And both of these metrics has f lambda as the Gaussian curvature and f mi as Gaussian curvature and h lambda as the Geodesic curvature. U mi lambda is strict local minimizing, then again you have this convergence. And what's happening with this function when the parameter goes to 0? So it's this that we want to analyze. Let's see, okay. So take two sequences of parameters, mi n and lambda n, such that this function, the derivative of this function exists at t equal to 0. Remember, this is a non-increased function, so it's possible to choose these two parameters. Just to specify, consider un this function, this non-local minimizer. The non-degeneracy and the stability of the global minimizer implies that this family of solution blows up. Otherwise, you can extract up a subset. You can find that this sequence of solution converges to U dot, which is not possible because the global minimizer is stable, right? Then you know that this soup diverges to infinity, right? So for technical reason, remember that we have this three condition, and for technical reason, we consider more two condition here. The first one is that the maximum point of f and h are the same. Then the maximum is on the boundary of the manifold. Remember that the set is that the Euler characteristic is negative, then you have at least a three component of the boundary. For example, here is your manifold. So the maximum point is on the boundary. Is the maximum point, right? And also, this max point are non-degenerated. The second derivative at this point is not zero, and also it's critical point for f. So since f is defined in the manifold, the max point is the boundary, we consider that the maximum point is critical. Then a point in the manifold is called a blow-up point for these sequences of function if for any positive radius you have that this loop goes to infinity. So if for any a point is a blow-up point, if you consider any ball, it's fixed radius, and then the slope of the norm of the function un goes to infinity in this ball, no matter the radius. Bom, so the first thing that we prove is that this family of solution is bounded from below, and this is just you consider the solution of this problem, considering this family of solution, and then what you get is that for some positive a, we have this condition for this function phi c, and then you can apply to the maximum principle to obtain that for all n you have this estimate, so you get this lemma. So the family of solution is bounded from below. So this implies that the soup of un on this ball, if it's a blow-up point, goes to infinity. And also, for any compact domain on this set, I mean, remember that the maximum point, the function, are less than or equal to 0, and the maximum point, the point when the function is 0, is on the boundary. Then, if you take a compact domain, a domain such that does not have any maximum point of f in the H, then in this domain, the family of solution are uniformly bounded from above. So this implies that if the point P it's a blow-up point, then the point has to be one of the maximum points of the functions. Let me skip this. So what you have as a consequence of this two lemma is that if P is a blow-up point, then f and h has to be 0 at that point, and the function has to go to infinity. So the main result that we found is the following. There exist two sequences goes to infinity, goes to 0, sorry. A sequence of functions, sorry. Yeah. A sequence of function in M, a finite set of points in M, one sequence of numbers goes to 0, and another section of point on the manifold converges to this point, such that UN are non-minimized critical point of the correspondence functional. The corresponding metric has F(m) n as the Gaussian curvature and H lambda n as the Geodesic curvature, and they have total curvature uniformly bounded. I mean, you have that the integral of the norm of F(m) plus sorry. Is uniformly bounded. And the sequence of function converge at least smoothly on this set to some smooth function. The corresponding metric, corresponding conformal metric given by this conformal factor U infinity, it's complete. M infinity, it's M infinity, it's M minus the block points, which is the maximum. Not exactly the maximum, but it's some of the maximum of the function f and lambda. And the metric G infinity, it's complete. If you have the manifold minus some finite set of points, right? And it has finite total curvature. It's easy if you have these estimates. Just take the limit. And you give a precisely description of the limit how this convergence happens when UN goes to U infinite on the neighborhood of the point here, which is given by this last item 5, and this difference converge in some small neighborhood of the block point to this function, and this function gives us conformal metric to the Euclidean metric on this set. It's a half space which has the C infinity as the Gaussian curvature and D infinity as the geodesic curvature of the boundary. The relationship between me and lambda n is given by this convergence. This quotient goes to 1. This metric, as I said, it gives us a conformal metric to the Euclidean metric with the Gaussian curvature, the constant C infinity, and the geodesic curvature equal to the infinity. And satisfies this estimate. It's the volume of this metric. Right? It's less than equal to pi. And also, n, this capital N, it's the number of the block point. We can estimate the number of the block point, which is related with this constant C infinity and D infinity. The quantity of the block point it's at most 3, which depends on the value of the C infinity here. If C infinity is equal to 0, then you have only one block point. Always has to have at least one block point. Always. But if C infinity is bigger than 0 and less than equal to 1, and the infinity equal to 0, then you can have 1 or 2. And otherwise you can have 1, 2, or 3 block points. This is obtained by the estimate on the volume here. Compare with the whole volume of the manifold. How many time? 10 minutes? Okay, thank you. Let me give an idea of the proof. So we choose two sequences of parameters which goes to 0, satisfy these 3 conditions. This is a technical reason why we choose this in this way, but it's related with something that I said before. I will not explain in detail about this, but we choose first that this derivative exists, and we consider the corresponding non-minimized critical point UN that we found before. And the estimates on the total curvature follow. This estimate here follow by these two estimates on the level of the energy of this guy. And by this estimate, with, which I said as we found. Then you have to analyze what's happening in a neighborhood of some block point. You consider a sequence of points on the manifold in some neighborhood such that the function attain the sup, the maximum in this ball. This point xn, it's in the interior of this ball, and converge to the infinite to the block point. So we divided this analysis into 2 cases. The first case is when this quantity goes to infinity, and then you normalize the function in this way, which is less than or equal to 0, exactly Wn in 0. And then we don't know yet if the blow-up point it's on the boundary or in the interior of the manifold. But if it doesn't matter for this if it's on the boundary or if it's on the interior. But because what we get is that if this happens, this convergence in C2 lock of R2, then we find a contradiction because by the result of Shenlin, the limit W infinite has to be this function which satisfies these estimates. But what we have, we can prove that if this is the case, then the integral has to be less than 4 pi. This gives us a contradiction. So this convergence cannot happen. So if this convergence cannot happen, then the convergence happens on the half space. And then happens in the half space with this condition on the volume on the integral. And by the classification results by Liu and Zhang, we found that the limit is exactly what we said in the theorem. So this case, it's essentially this. When this quantity goes to infinity, what about if this quantity is bounded? If this quantity is bounded, uniformly bounded, then you will use the Eckland's variação princípio to find a point. Remember, in the first case, we consider the let me see. Okay. This xn is the sup of the function in the ball. In the ball is centered on the blow-up point, but in this case we need to use the Eckland's variação princípio. Otherwise, you cannot prove that this sequence, this function, this normalized function is uniformly bounded from above. Right. Use this variação princípio to found this point. And then you use the theory of regularity to prove this convergence in the half space. Now, when the half space, exactly. And this limited W infinite satisfies this PDE with this condition here, right? But then this is not possible. There is no solution of this PDE with this condition, with Liouville type result, which we gave a proof of this. It's this one. If you have a matrix of the order 2 negative definite, then there is no solution of this PDE satisfies this condition in which is bounded from above on the half space. The idea of the proof, it's considered, you can write if there is some solution, you can write the solution in this way. And then you can do some estimating to find that this limit is bigger than or equal to 2. And the function is bounded by this quantity goes as the log of the norm of the point. And then after many computations, we found that this integral is equal to d minus 2, but by our assumption that the metric is negative, we found a contradiction. This integral is negative, but it has to be positive. It's a contradiction. In this way, we finish the proof of this case. Then, as I said, we divide the previous results into cases. When that quantity goes to infinity, we found that convergence. And when that quantity is bounded, when it's bounded, there is no solution because it converges to nothing. Okay. The paper that we consider our motivation, we extended the result by Boré, Galimbert, and Struve. They did this for the closed case. In fact, the existence of multi-solution, when you consider a perturbation of the function, was already knew by the work of Dig and Liu, but the technique that they used does not allow them to prove that what's happening when the parameter goes to 0. Then Boré, Galimbert, Struve in the 15, they use this technique to give this description of this family of solution in the closed case. But only gave the two conditions when that quantity goes to infinity and when the quantity is bounded from below, and then after is to prove that the second case cannot happen because of the Liouville type results. This result was extended for other sets, for the curvature set, and the Story Roman use this technique to extend these results for any dimension for the Yamabe equation, which it's not so easy to do. And the Manuel Dopini and Roman, they construct solution in the closed case in this phase, in the closed case, to found the metrics that with prescriptions with blow-up points prescribed. This constructs explicitly this family of solution. And the Liouville type theorem was extended for other sets. You can see in these two works here, and our work it's acceptable to. You can find it on archive. That's it. Thank you.
I have one. I think. So in the case of if we consider the boundary case, do we know for the case with positive Euler characteristic any explicit examples of families of curvatures in geodesic curvatures that do not admit any, you cannot prescribe them?
As the closed case, that we cannot prescribe 1 plus epsilon x. Yeah.
Explicit examples?
I think it's similar to that because when the Euler characteristic is positive, we have on the disk.
Yes.
I think that is also a causal order obstruction for this case. It's similar, I think. At least you can consider, for example, the geodesic curvature equal to 0.
Oh, no, yeah. In this case, you have, but I mean, if you have something that has some sign in the geodetic part.
Okay. Mix. It's not necessarily 0. I don't know. I don't know. I don't know if there is this obstruction.
Because I mean, the whole thing with the boundary case is that the things will cancel out, and you have more possibilities to prescribe stuff, right?
Right.
So, yeah, I was thinking
when you take a general function, it's difficult to deal with this case.
Okay.
Case that in the closed case it's closed, in the bounded case it's still open. Yeah. Welcome.
Thank you for the very nice talk.
Okay.
And could you give an idea why you have the non-degeneracy of the critical points of the boundary, and maybe it's related with if you could show the maximum principle you're considering?
You mean in the first result? These results? No. It's direct. A calculation if this derivative in the estimates. Yeah. Then, yeah. You mean when you take the perturbation of the function? Yeah, because with this condition, if the non-minimizing converge to U0, at some point it has to be a minimum point. Yeah.
You mentioned that in the closed case, there are works in which they prescribe the blow-up points, right?
Right.
Is there anything like that for the boundary case? Specifically, can you run like mountain pass in a way that these solutions converge to blow up and prescribed points?
Yeah, yeah. We are trying to do that. I think so. Yeah, yeah, yeah.
But with variational techniques, it's not known.
No, using this technique, I don't know. Even in close case, it's different. The technique they use. One thing that I want to mention is that the function f and h can have a lot maximum at the boundary, but only three of this boundary will be the block points. So I don't know how can you
don't know which ones can
you
have
don't know which one can have the block. Yeah. Yes. Yeah. Yeah.
Okay, thank you.
You're welcome.
One more. Almir, thank you for your.
You're welcome.
What happened if you take in account more points, more singular points? Because in the results you have maybe one or two or three, and
Yeah, this it's a
that-
consequence.
Ah,
It's a consequence. We first we prove that the number of block points it's finite. Then with this the method on the volume that we found, we can prove that the number of the block points it's at the most three. Even if the function has a lot of points, many maximum points.
and okay, all these technique, the results works in dimension 2.
Yeah.
Okay, and use the Gauss-Bonnet for equation for what happened, or if I don't know, it's a curiosity question. Maybe in dimension higher,
Hiding.
the generalized Gauss-Bonnet form,
Uh,
but with the by tensor, or I don't know,
who,
or it's
who studied this case for the Almir equation? It was Angela Pistoia and the Roman. The second. Yeah, but if I mean, remember, they could prove that the solution is not, it's stable. I think they put it as assumption. More than true. Yeah.
thank you.
You're welcome.
Okay, thanks again for me. Sorry. In Zoom, some people has a question.
Okay.
Thanks again.
Thank you. Wait.